So this talk is not about a specific science result. This talk is about our efforts at NCSA to play our role by doing data management for a phase 3 dark energy cosmology experiment. So to start off, I just wanted to summarize what I'm going to talk about in the rest. What good was blue waters to us? The answer was it's extremely helpful and crucial for a component of our science, which involves doing a weak lensing calculation, which I'll explain later. One of the things that blue waters really helped us with is we got done in 2 weeks, would have taken us 6 to 9 months to do on all of our other computing resources. And we're doing production that we have to make deliveries to the overall experiment of many data products. And this was important in actually making deadlines. And we need a similar capability to do our final release. We're hoping that maybe we'll get it done by the time blue waters is still around. So what is the Dark Energy Survey? It's a phase 3 dark energy cosmology survey. It is going to probe dark energy by the things you can do with optical astronomy on the ground. Namely, the 4 probes are galaxy clustering, how galaxies cluster or don't cluster and create voids in space. Weak lensing, which is a technique I'll explain a little more about, but allows for a mass map of the universe to be created, including sensing the dark matter. Large-scale structure, which again is like a standard candle, and supernovae, which you probably understand, large-scale structure, which is like a standard ruler, and supernova, which is like a standard candle, which lets you tell how far things are away. The basic plan was to do 2 surveys, a wide field survey over a good portion of the southern sky looking out the galactic cap of 5,000 square degrees, and a supernova survey of 30 degrees squared. Why is it only so small? Because we keep on visiting those areas over and over and over again. The plan of the survey was for 5.5 years. The survey is done observing. And the basic instrumentation is the 4-meter Blanco telescope at the Sierra Tololo Observatory in Chile, and DECam, a 512 megapixel, 3 degrees squared camera. So 3 degrees squared, to give you a sense of scale, it's about 4 times the width of the moon, is what the field it can sense. The photograph on the right gives you a picture of the DECam when it was being built at Fermilab with one of the prominent scientists next to it, and it gives you an idea how big it is. And also I want to convey to you that it's in layman's terms, it is more of a wide-angle photograph compared to the Hubble, which would be like a telephoto. So the point is it captures a wide field of view. So now, who or what is the Dark Energy Survey and where do we fit into it? Well, we're in what is in the middle of this picture. The Dark Energy Survey had its instrument on the Blanco telescope. The Dark Energy Survey rotated an organized bunch of observers who are also the project scientific staff down to actually do the observing and to do it in a kind of rigorous procedure-based way to assure that the observations over all 5.5 years were taken under similar circumstances, right? And the observations also included Fermilab for DECam support, and of course the CTO site for the support of the telescope and overall day-to-day support of the whole survey operations down there. NCSA is in the middle of data production. I don't have a photograph of all the staff, so I put a photograph of the lead production scientist, Robert Grundle, right? We have a staff of research scientists, operations staff that work in our framework, and we're supported by technical services from all over NCSA. And of course, the software that we run is not stuff that we just invented, but it's contributions from many in the collaboration and indeed from open source astronomy software. Then lastly, of course, there's data, but what's data without knowledge? Here's a photo of some collaboration meeting. And the point is there are more than 400 scientists funded by the US DOE and a various number of international partners. So in the middle in data production, we produce a bunch of standard data products. We do custom data processing, and our basic job is to keep the collaboration happy by doing large-scale data production. So what is it, what are the pipeline architectures and what are the data products that we produce? This is a kind of picture of our processing system. I've drawn a line across it. The top part is prompt stuff that had to be done every night, which ended up supporting the supernova science because, as you may be aware, supernovas are luminous for about 30 days. Type 1 supernova reach the same maximum brightness, so they're good standard candles. And it is a bunch of processing that just has to get done every night, and we have to keep up with the fire hose of data coming from the telescope. In our era, that is about a terabyte of uncompressed data, or about a half terabyte of compressed data. On the other hand, we have a batch world that services the rest of the data products needed to do the survey science. And indeed, the codes are much more complex. And the usual matter, the way processing normally proceeds is to do something like an annual release where we reprocess the whole integral of all data that were taken and do it with best calibrations and best software at the time, and then release it to the collaboration. Underneath that is a technical services architecture. I've drawn kind of three major components. The first one is the nightly processing engine that we needed to get the real-time processing done. As I'll point out, we're now done with that. That was successful because we're done observing. Over to the other side of the diagram is the offline processing engine, and then on top is collaboration accessing services. And if you notice, a lot of those components are actually repeated, but the truth is they more or less operate as separate systems talking through data. In particular, we keep our central store at the NCSA storage condominium. We can use any of the computing engines we've seen there that is best for the task, some combination of best for the task and actually being available. Blue Waters is a very important computing system for us, but we also use the Illinois Campus Cluster and remote computers at Fermilab for FermiGrid since they're a collaborator. Data products file-based data products are stored in a big GPFS file system surrounded by VMs, but also it's astronomy, and astronomers like tabular data, and they like relational databases, and we have an Oracle rack cluster that has half a terabyte of table space. Right, the same system infrastructure and the same framework is reused in the offline processing. Right, online processing is deadline and throughput and deadline oriented. Offline processing is merely throughput oriented. It doesn't have to be available every day as long as you can make your goals. And then we have a bunch of collaboration access services. The job management that we use is adapted to, it works on Blue Waters, but works on all the computing platforms. We treat them all in a uniform way. And in Blue Waters in particular, one of the issues in using an HPC system is they like large jobs, and they like to give you many nodes, but they do not want to hear from you every second when I want to spawn a short job. So basically, we use a kind of classic architecture, if you're familiar with HT Condor, but if not, I'll explain it a bit, is that in general, the offline is organized in campaigns, namely process all this data and get this done and build a data set. Please do it quickly, but you don't have to do it minute by minute. What happens in our system is that we, using the pointer here, I guess. Oops. Help. Hit the what? Okay. What we do is we start a campaign nanny, which is a body of software that stays kind of alive during the whole campaign. One goes to Blue Waters and one asks for some number of nodes. Blue Waters gives the nodes back. The campaign nanny waits for a free node. And what we run here is not the overt workflow. We run a program here whose main job is to go back and contact the campaign nanny and say, I'm free, I would like something to do. The campaign nanny actually gives it the real job, and it executes the job, and it quits. The node itself comes and quits and says, do I have enough time left to do anything useful or not? If it's done, it's done. If not, it goes back, and it does the job again. In the meantime, it acquires its state from our central store of databases and files, does its computations, and pushes the new data back into, I'm going the wrong way. Oh. Back into the system. So that is a way that one executes many small jobs in an environment that's tailored for a few number of big jobs. And it works successfully at Blue Waters, and it's a system that we use uniformly on all processing platforms that we use. The Blue Waters specific integration topics, well, what was it? What did we really need Blue Waters for? We needed to satisfy computing needs that we had, that there is no way that we could have done on the Illinois Campus Cluster on our location or FermiGrid but do it with minimal framework differences, i.e. have it make it work in this kind of system that I just talked about. The primary challenges involved were the large number of outbound connections DESDM jobs made due to both the fact that we use this system called Condor that makes outward bound connections. For example, the callback to say, please give me a next job to do. And database integration is that we upload all the detected objects that we detect into a database. To give you a sense of scale of how large our tables are, the Dark Energy Survey detects about 300 million galaxies. Okay. And so the issues are many small jobs, but that's solved by this kind of Condor scheme, turning it into one big job. And the file system load. We make many small files because we integrate community codes. And so we're always doing I/O when the codes in a pipeline talk to each other, and they all need a variety of files. To give you an idea of what the challenges are, this is a slide that kind of shows in false color with exaggeration of what a raw image looks like. And of course, the pretty picture that you all like to see is on the other side. This kind of processing we do. But this is really where Blue Waters has shined in this matter of weak lensing. If you can kind of look at the photograph on the right side of the picture, you can kind of see how the galaxies are oriented around a spiral. And that's because the shapes of the galaxies are warped due to a presence of dark matter between the background galaxies and the dark matter or the mass that's present in the foreground. The cartoon shows the kind of difficulties that one undertakes. There's a circle with no ellipticity. There's what the cosmic shear or the gravity does to it in a sense of scale. Then there's the ellipticity of the galaxy itself, and then there's the final product. And of course, that's just what's going on above the atmosphere. Also, considerations are the fact that the focal plane is not, the instrumental response is not the same everywhere in the wide area focal plane. And for example, the point spread function varies from place to place. So the problem in tracing out this signal in code is very complex. The codes are complicated, state-of-the-art, and are optimized for functionality as opposed to performance. So Blue Waters, where it really shone for us was to get done in 2 weeks, a weak lensing run that would have taken us 6 months on everything else. We used about 3 million core hours. It was the multi-object fitting code that does the weak lensing. And the observations included 3.5 years of observation, so we processed 3.5 years. We have to do this again this year or early next, where we'll have 5.5 years of observation and the computations will get bigger. And otherwise, we're able to use Blue Waters, partly to commission them for this, but partly because it's there and available to do more kind of ordinary science. I'll say also that Blue Waters has been useful to us. Blue Waters used when DSDM has many campaigns. Other compute resources are unavailable because of maintenance and upgrades. So we've used about 1 million hours for other data products. The opening speaker made a comment about how the worlds of cloud native computing, HPC, don't talk, and I made this slide in kind of response to what I heard in the opening, which is that our project as a whole manages to talk to 3 worlds. We have a high throughput component that's our overall architecture for batch processing that lets us use many sites. We use 2 HPC clusters as our primary resource, but we also use cloud native architecture over in collaboration access services. And so at the level of an experiment, we're able to talk to all 3 worlds and find a useful place for all of them. I guess I wanted to show that because it struck me. I'll point out that what makes this all possible is the fact that our storage systems are autonomous and independent of all other pieces. So the technical basis for existence of all these 3 things is cloud cultures. I'll skip this because I talked about it already. And I'll give you a sense of what we do in the data distribution system because it's a collection of stuff that we have to serve the collaboration and provide data access for them. And it kind of looks like this in architecture, which is again enabled by GPFS and the data stores at the bottom. It's decoupled from the production systems in that way. And we have all this kind of nice containerized stuff that gives people access to data. I have about 1 minute left. Okay, so I'll go to the summary. Right, Blue Waters is absolutely crucial for DESDM's most cycle-intensive processing needs, and we have another need to reprocess our year 5.5 and 6 for the final processing of the survey. Blue Waters also played a role in ordinary processing in Dark Energy Survey. We have about 800 million, we have about 88 million CCD level images that we've processed in toto. Blue water is also useful to us because we've processed over 1 million DECAM images for non-DS processing in NCSA, stuff that's outside the survey boundary, but we were doing for other purposes. Blue Waters was able to integrate into processing framework like ours, and ours is more like high energy physics experiments used. It's based on HT Condor. We have these extensive transfers and communications into and out of Blue Waters. And what has been absolutely outstanding in the support that we received is in order to support these large number of connections, Blue Waters had to go back to Cray and get system level changes, which they did for us. It took a while, but actually enabled the kind of processing that we really needed to do to get the scientists their data sets on time.